Hello, welcome to actually a problem session. Today I want to cover a lot of ground. It's all about resistive circuits. So what is a resistive circuit? Resistive circuit is a circuit in which you only have resistors and voltage sources, okay? Voltage sources or current sources. So you only have resistors, and we'll just call it voltage sources. And often these voltage sources are direct current voltage sources. Means if the voltage source, the current that's flowing is fixed. It's not going back and forth. It's not like sometimes going that way, sometimes going that. No, that's not the case. That will be alternating current source, and we'll do that some in the future. We just want to do a steady current situation. So this current is so this is one thing, and another thing is the current is steady, not changing in time. EMF or the voltage is also steady. It's not changing in time. So these are the things you want to know. That those are the behind some assumptions to lay out what kind of problems will do. All right. What is a resistor? A resistor is basically you have a conductor, like a wire. You can buy resistors, resistance elements, where especially manufactured conductors which have a specified amount of resistances. So resistors, we will just say, is defined by having a property called resistance. Okay, so there is a property called resistance, and we'll denote by letter R. And this is the property of resistance, that if I apply a voltage difference across two ends, then a current I will flow through it and will have this relationship. This is what you call Ohm's law. And then in the circuit, you can also have a voltage source and such a battery. This can be like a battery. An example is battery. So inside the battery, maybe you have a conductor here, and on the side there's another conductor here. So this is like this could be plus, and the body can be minus. So the current will be flowing from this to the side, and all this current added up is like that way. Inside there's a current that flows inside, and the same current must flow outside. So that's a battery. Okay, so this is in isolation, and we will solve the problem. So all the problems are we'll go with given a circuit. So given a circuit, for instance, like this circuit. So you have R1 and R2. I can combine them at some point A, and then you can connect them to point B here and point C here. So I'm using this notation of battery. This side is supposed to be negative, this side positives, like in this battery where the body was kept negative and the center rod was kept positive. So this positive and this is negative. So you can indicate something like this way, and so it's point C I've connected. So there are like three places I've connected, and these wires, these wires that I use to connect them, we assume that this resistance is already included in here. already included in the value, say R1, and this is another one, like over here is connected it, so you can see this already included in this is R2, R1, R2. So the question is, if a circuit is given, then what we want to know, so you have an EMF here, so we want to know what's the current going through each one of them. Okay, so one thing, find current through each element. Each element. This is one element, this is another element, this is another element. So how much current is going through each one of them? Another question is, what's the voltage dropping across them? So what's the voltage drop across this element? What's the voltage drop across this element? What's the voltage drop across this element? So this one is actually already given by the original relationship. So what are voltage drops across each element? Now you can see that these two questions are kind of related. If I have this resistance, say your resistance is given, and you found the current. You found the current. Then of course you can find the voltage. This will immediately tell you what the voltage is. So this can be obtained from that. Now say you don't know the current, you know the resistance, and you found VA minus VB, just drop. From this, obviously you can get the current. From this you can use this to get the current. So finding all of this is equivalent to finding all of this, and vice versa. So there are two techniques actually, to focus on finding this or focus on finding that. Okay, and I'm just gonna do focus on finding the voltage drops, and once I get the voltage drops I can find the current. Okay, and sometimes you can mix the two, depending on the context. So let's do some problems now. This is the theory. Okay, so there are basically three types of problems. One is where maybe I would say 4 types of problems. So let's do a little bit more fine-grained. So one is you have one voltage source, and resistors are connected in series. Now this connection is what defines, like one after another. Let's say there are 3 of them. This is R1, R2, R3, and then you connect them through. Again, the connection wires have no resistance, they're already included in there, and this voltage is some E. Okay, now first thing to notice is there is say the current I is here. Say I don't know this value, but this current I is here. Now this wire carrying current is there's no branching taking place. The same current will go through here, same current will go through here, same current will go through here, and so the current is going to be same throughout. Say this point is say A, this point is B, this point is C, and this point is D, and so all these points have the same potential. So this will be, because negative, we're going to take this as potential at, so this all of this is the same potential. So V sub D, we can always set one of them to be 0, and that will be the negative of one of the batteries, not all the batteries. So one battery will have a negative set. So this is the choice. I can make one choice for the potential. That's like a reference electric potential. And this side is all of this going to have the same, will be at L1 potential, because there's no resistance here. We assume this resistance included over there. So this is somewhat mathematical, right? It looks physical, but we're assuming these wires don't have any resistances because they're all included in here. Okay, so we can just call this all of this will have the same potential. So potential at A will be E. So this is 12 volt. Let's look at a concrete example. So this will be 2 ohm, this is 3 ohm, and this is 5 ohm. Okay, so let's look at that example. Well, for each one of them, I can actually write down, we don't know what the potential will be here, we don't know what the potential will be here. So if I could find these guys, I could just solve the problem, that and the current. So let's see. So for R1, if I look at this one, you can write down the equation as VA, which is 12, VA minus VB. First, VA is 12, V sub D is 0, VA minus VB is I times R1, and VB minus VC, VB minus VC is I times R2, VC minus VD, VC minus VD is I times R3, VA minus VD is this E. You can see right away, if I add all of this up, I get a VA minus VD equals to I times R1 plus R2 plus R3. So I can get the current right away. This is 12, and this is I, and this is added up to 10. So then I is 1.2 amp. That's already found out the current, and I can use in one these guys to get the voltages. So VA is 12, and VB I don't know. It's 1.2 times 2. So that tells me what VB will be. VB will be 12 minus 2.4 is 0.6, and you have 11 minus 2 is 9.6 volt. So at this point, if I stuck a voltmeter between this point and this point, if I stuck a voltmeter with these 2 points, it will have this as a reading. So basically 2.4 volt, 2.4 volt dropped across this. How about VC? So I now know VB, so I just apply over there. 9.6 minus VC is 1.2 times 3, so is 3.6. So VC is 9.6 minus 3.6, and that just that's a 6 volt. So if I took a voltmeter between here and here, it will have a reading of 6 volt, because the other side is 0, so this point is 6 volt. VD is of course already by choice we picked that to be 0, so we can confirm that that's 0. So VC is 6 volt minus VD, so we didn't know, and I is 1.2 amp, and R3 is 5, and this is 6, so VD equal to 0. So this is a circuit, very simple circuit, and we're able to get all the voltage points. Sometimes when people ask questions, they also say, okay, how much power is being dissipated in each one of them? Like these resistors will start to heat up, and they will heat will get dissipated. So power dissipated is a side question that can be answered now in, say, resistor R1. So R1 is going to be I1 R1 square, and so that's just going to be equals to 1.2 times 2 square. So 4 times this many watts. So that's the rate at which it is giving out the power, and P2 will be similarly 1.2 times 3 square is 10.8 watts, and P3 will be 1.2 times 5 square is 1.2 times 25. 25 times 2 is 50, and 25 times 1 is 25 plus 5 is 30. So this battery is actually must be producing this, supplying this power, right? So this energy used per unit time from battery will be just sum of these guys. So 4.8 plus 10.8 plus 30. So you have a 40, 44, and 45. This many watts. So that's how much energy, chemical energy inside the battery is being used per unit time. So this is same as 45.6 joules per second. So sometimes this kind of thing gets asked, added at the end of the problem. But if the circuit is concerned, this is a simple circuit. Okay, let's do a little bit more complicated circuit. Okay, a circuit like this is called, resistors are connected in parallel. Why do we call it parallel? It looks like parallel, right? So that's one way to say it. But actually, even if they didn't look parallel, it will still be parallel as long as you can see that the current that's coming in to this structure that's we're calling parallel is actually dividing up. So the current is dividing up into 3 branches here, and then those same 3 branches and is joining again. So if you think of this structure with this parallel knot, the way you decide is the current comes in, divides, and those currents combine when they get out. So even if you drew something like this, they're not, they may not look parallel. They definitely don't look like a parallel drawn like that, but it is the same thing. It's dividing into 3, this structure, and those 3 currents combining in over here. So if you call this current I1 and this current I2 and this current I3, then this I1, I2, 3 come together and join again. And so this current, say total current is I. So I must equal to I1 plus I2 plus I3. Now, do you know why? Well, because there's no charge accumulation. Current is coming in, means charge is moving, but there's no place charge is accumulating. So because these are steady currents and currents are not accumulating at any point or depleting from any point, so there's no source of current here. So like when you had suppose you have a capacitor, then the current will be, a charge will come and kind of dump onto one of the plates, right? But here it's charge can build up, but here is no place charge is building up. This junction, there's no charge building up. So you can have a current coming in, has to get out somehow, and the same one can combine together. Now this is parallel, but here is something that will not be parallel. So this looks like parallel, but suppose I go here and I maybe have two of these guys, so these together becomes a parallel. But let's see, I had one more with these guys. Let's draw it like this. So there are four parallels, right? So this whole thing is parallel. If I think of all these four things are parallel, if I think of this as one combined thing. But suppose at this point to this point there was a connection. Now this will be a this entire circuit will not be parallel because of this connection. So this kind of circuit is called bridge circuits, and we're going to do one example of bridge circuit. So we're not talking about this kind of thing. We're talking about very simple parallel circuits. Okay, let me erase up this and then try to do this problem with some numerical values. Okay, so back to our parallel circuit. So we have this is one equation we can immediately get. So we want to get all the currents. So we want to get the four unknowns here. Okay, assume that this is, say this is known 2 ohm, this is 3 ohm, let's call this 5 ohm. These are kind of randomly picked numbers, so say 12 volt. Okay, now let's look at how many voltage points there are. Okay, so in this circuit, if you call this, say, A, point A, and call this point as point B, then all of these points are all one potential. So they all have potential VA. On the other side, if I go on the other side of these guys, this is important for you to kind of understand. All of this, the resistance here already included in these values. Okay, and you can consider the resistance this to be 0. So this all of this is at potential VB. So there is no potential there's no unknown potential here. So VA is 12 volt and VB is 0 volt. So this side is negative, so we just just set it by convention, just pick it. This was the negative of the battery, this is the positive of the battery. So now you can immediately get all the currents. You can get I1, I2, I3 very nicely. So what is the I1? I1 will just simply be what's happening across here. So if you look at this resistor, this is 12 volt VA, so VA side, and this is 0 volt, and this is 2 ohm, and this is the current I1. And so this is 12 minus 0 over 2 ohm, this is 6 amp. I2 similarly is going to be 12 minus 0 over 3, 4 amp. And similarly, I3 will be 12 minus 0 over 5, 2.4 amp. And so I is the current that's going through this current through the battery. Current through the battery is in the outside, which has to go through the battery, and this has to combine like this. So just have to add up 6 plus 4 plus 2.4 is 12.4 amp. Okay, you can similarly answer the question about So how much power this guy is taking is 6 times 2 square is 24 watts, and power this guy is taking is 4 times this is not correct. I is square R. So am I doing opposite? Yeah, I'm doing opposite. So I square is going to be 6 square times 2. So this is 48 watts, and this will be 4 square times 3. This 72, and this 48 watts, and this P3 will be P is I square R. You can also say I times V if you kind of remember this, and V equals IR. So this is, you should remember this formula. And this is going to be 2.4 square times 5, and so this is like a 28.8. So the total in the battery is, if you say P1 plus P2 plus P3, must be supplied by the battery, right? So this plus this is 72 plus 48 plus 28.8. So this is 0, 120 plus 28.8 is 148.8 watts. Now if I look at the battery, you have a 12.4 square times 12, and that should equal to IV. So this is for battery, you're gonna get an IV. So how much current is flowing is 12.4 amp times voltage was 12, and this is also going to be 148.8 watts, which is the same as that. So okay, so this is just ancillary, is problem that shows up, but circuit solving is just called finding the currents and finding all the voltages. Okay, so once you find all the voltage, you can immediately find the currents and vice versa. Okay, let's do another more difficult problem. Okay, so here is something that you can see the different parts. Like if I think of this as one resistor of 5 ohm, then these guys are in series, but this is in parallel with this, because the current comes in and divides, and the same current combine. So if I call it I, and then this is I1 and this is I2, then this is I1 and this is I2. And then over here, what comes out is what went in. So this is also I. And then the way it's here, this I comes in, and then this I has to go through that. All right, this, let's call this 12 volt battery. All right, so what will be what kind of problems can we ask on this? Okay, so one is you can look at that from all of these points, which you haven't gone through the resistor, right? You haven't gone through resistor or any battery or anything like that. So all of these points are one potential. So if we call this A, then this is at VA. So this is minus and this is plus. So we can call this guy a 12 volt, and this side will be 0. This will be 0. So all of this will be 0. But not all the way here. This is B and this is C. So this will be all one potential. This will be all VC, which is 0. But then there is this point, which is that's the B, and we don't know the value of the B. B is not known. This is not 0, okay, because you go through the resistor. Okay, now we need to figure out, just if you think of the voltage, there's only one voltage unknown. So just VB is the only thing we need to figure out. In terms of current, we need to figure out current I, I1, and I2. That's all. There are 3 currents and 1 voltage. But we know we can settle the problem either way, right? You can do it voltage or current. So let's set up voltage. There's another voltage actually. I forgot over here. Equals, let's call it BC. I'm going to call it D here. So the VD is also unknown. Okay. So I'm going to just set it up like this. Okay. Let's set up all the V problems. Okay, just voltage problems. Or we can set up current problems. Let's set up just voltage problems. So voltage problems will be VA is 12, VC is 0, VA minus VD. VA minus VD is the current through I1 through R1. So 2 times I1. I'm just going to use 2 ohm for that guy and 3 ohm for that guy. I'm just going to do numerically here. And VD minus VB is going to be 3 I1 because same current I1 must go through both of them. Then VA minus VB. VB is 5, but this time is current I2 is going through that. And then you have a VB minus VC. VB minus VC is going to be current I goes through 7.5 times I, and the current is I equals to I1 plus I2. So it looks like a whole bunch of unknowns and things like that, right? So but there's only VB and VD that's unknown, and you can see that I can eliminate all the I's. There are several ways to proceed the algebra. So you can put this as over there, and then you can get a VB minus VC equals to 7.5 I1 plus I2. Now you can say I'm going to get rid of all the I2s. Okay, so VC is 0, so VC is 0, so just get rid of that. So here is a VB is 7. So VC is 0, so VB is that, and so you have a VA minus VB. So you can just say, hey, I want to think of this as wherever I see I1, let's call this over here. If I add these up, and I don't want to solve VD, so VA minus VB is just going to be VA minus VB is going to be 5I1. And VA is already known to be 12, so don't need to carry that. So we can just, from here, you can write down in terms of, this is 12 minus VB equals 5I2. So I can see that if I add these two guys, right? So this will be 24 minus 2VB is 5I1 plus I2. from here and here I can get one equation in VB, and that would be VB equals to 7.5 times this over 5, 24 minus 2 VB over 5, and then you can solve for VB. Okay, now once I solve for VB, I can solve for that means I already found what's over here, what's over here. So how do I get for VD? So it's very easy to get VD now, right? Because if you look at this thing, you have a VA minus VD is 2I1, and if you have a, so this divide by 2 over here, and you have this is 12, and then you have a VD minus VB over 3 equals to I1, and so if I combine this will be 12 minus VD over 2 equals to VD minus VB over 2, and so I already got VB. I put in there and solve for VD. So this is the one way to do it without actually invoking any more laws or anything like that. I just list all the relation I can get for each one of the elements, and then this is for a junction where the current combines, and then we just look at the equation and try to solve it. I'll leave these you know, as an exercise for you to solve. Okay, so this was a lot of different types of resistive circuits. I think when I stop here, the video is already about 37 minutes long. And just to remind you to not forget to subscribe to this channel. If you like this explanation, please hit the like button, and you can check more out at this website. Okay, see you in another video. Bye.